Sorry, will you give me the go ahead? Okay.
Yeah, it's fine. So welcome to today's NFDI talk. This episode is about metadata integration. The speakers will showcase how datasets can be described with domain-specific meta using SchemaOrg as JavaScript object notation for linked data, using defined terms from terminology services, and how everything can be indexed in searchable resources. So Dr. Castro is team leader semantic technologies at the ZBMed Information Center for Life Sciences. She's a computer scientist interested in semantic web, linked data, data science, open science, and education, and currently involved in projects aiming to make FAIR a reality not only for data, but also for software and training materials. Dr. Neumann is head of the Computational Plant Biochemistry Group at the Leibniz Institute of Plant Biochemistry in Halle. The group develops tools and databases and in computational metabolomics uses bioinformatics approaches in plant research and advocates and supports the development of competences in data science and scientific data. Mr. Schneider works for FAIRagro, the NFDI Consortium for Agro-System Sciences, and is part of the Knowledge Management Department at ZBMed. He has a background in library and information sciences and specializes in research data management, metadata, and semantic web. So, welcome. The floor is yours.
Hello, everybody. So I think I will start. My name is Leyla Jael Castro. Thank you, Natalie, for the introduction. And thank you to everybody who has somehow participated in this presentation today that started in the Biohackathon Germany in 2023, December 2023, when we realized that different groups in NFDI were working already with schema.org to describe metadata about research artifacts. So let's going to move to the introductory slides. One more, please. Let's going to start with schema.org. Schema.org is about semantic markup for the web. What means semantics? Semantics means that what we observe in the real world, we give it a specific representation, the representation of the concepts that we observed in the real world, and the connections that these concepts have one to each other. For instance, we are seeing here that a movie is related to a director, to a set of actors, will have some reviews, will have some description. So this is all metadata, and it's semantic because of the way that we represent it behind the scenes. I will not go too much into details on how this is done. Schema.org at the very beginning had a big focus on e-commerce. And this is why if you go to schema.org, you will see that there is a lot to describe products and services. And thanks to this is that we get these nice summaries about movies, restaurants, when they are the most busy or not, prices, and all of these on the web. It has been very useful for this community, and the scientific community has seen that it is also useful to describe research artifacts. And in addition to the description of the research artifacts, if we do one more click, Gabriel, it is also useful to see if you are following some community standards. This one is, for instance, the community standard given by Google. Schema.org was created by the main search engines. It was useful for them to realize and learn a little bit more about the web pages that they were indexing and providing in the search engines. In the same way that they exploit this markup, the scientific community can also do it, and that is a big advantage. It's very useful for aggregators. We will see one about training materials later with Steffen. So let's go to have a deeper look into schema.org as a control vocabulary. So one more click. Yes. So here, it all starts with a concept that it is called thing. And from this concept, we have other sub-concepts. So we have here some inheritance. So everything is a thing. We have actions, we have biochem entities, creative works, events. Intangible, will not touch it because it's really intangible. Medical entities, organizations, persons. So you are seeing here already things that are useful for the scientific community. For instance, the creative work, the organization, person, if you want to describe authors of a scholarly article, which is a creative work. And we are already seeing here some more science-related elements, particularly for the life sciences community, such as biochem entity and medical entity. So these are what we call types, and the types are the concepts that we are representing. And on the right side, you are seeing some of the properties for one of these types, the type person. Here we can see that a person can have an address, and all of this is optional. So can have an address, can have an affiliation, can be alumni of an educational organization, maybe has received some awards, has a birth date, a birthplace, etc., etc. So we have types to represent the concepts, and we have properties to describe those concepts and connect one concept to each other. For instance, alumni of is connecting person and educational organization. Now, if we move to the next slide, we will see a little bit more on how schema.org has been used in sciences. Here, for instance, we have Science on Schema, which is an initiative focusing particularly on data sets and data repositories. So they are providing some guidelines and examples on how to use these two particular types from schema.org, data set and data catalog, to represent data sets and data repositories in science. The next slide is showing the CodeMeta project. CodeMeta is about research software. They also use schema.org as the basis. Here we can see some of the CodeMeta terms that they are adding to better describe research software. Next slide is about bioschemas. Bioschemas is another initiative building on top of schema.org. This one is supported by Elixir Europe, an international organization for life sciences. The approach is kind of similar to the previous one. So building on top of schema.org and adding guidelines. In bioschemas, these guidelines are called profiles that will provide examples, will tell you what is minimum, what is recommended, what is optional, whether a property should be always present and it should be only one, or you can have it many times. For instance, identification usually is one, keywords usually is many of them. And it provides documentation and examples about how to use schema.org in life sciences, but it also supports domain agnostic types such as data sets, software application, workflows, and so on. And with this, we have finished the introduction, a very broad, quick introduction to schema.org and some of the initiatives in science. Now we are going to continue with Steffen. Please go ahead.
Thank you very much. So the next will be an example that was developed quite some time ago, and it has nothing to do with chemistry, which I think is why it's very good to exemplify how this can happen in reality. Next slide, please. So let's have a look at training material. In this case, it's coming from the Galaxy Training Network, where Galaxy is some whatever software ecosystem. And for example, they have tutorials on computational chemistry. Next slide, please. And specifically, they have something on whatever molecular dynamics things. And here in the page, you see there is some header to the tutorial, and it has some structured information. Next slide, please. And if you go into the HTML or ask the SchemaOrg validator to extract whatever markup it finds, then you see that this information is also available in the structured way that Leyla showed before, also for the movie. Next slide, please. So how does it get there? This is actually a GitHub page or entry that is actually encoding the training material. So people are sending pull requests to add new pull material. Next slide. And at the beginning of that markdown document, you have exactly the little template of the structured information, and that gets rendered into the HTML page from the input. So what can we do if we have the metadata in the HTML page? Next slide, please. This is being harvested by the training e-support system, or TESS in short, which was also developed by the Elixir people. And TESS will harvest information about courses, events, and training materials, and then allows a particular search over that. Next slide, please. So you would have a normal search page. Next slide. And you can find the cheminformatics training course that we saw earlier. Next slide, please. And then you can organize that into tables or maps to present that to the users. So this really nicely shows how we can embed metadata and then use it for something useful, so you can check what training courses are nearby to your institution in the next half year, for example. Okay, that was the example on training material. And now, next slide, we go back to Leyla, and she'll show NFDI for data science usage of SchemaOrg.
Thank you, Steffen. So let's go into see some of the examples that we have been working with schema.org as a basis in NFDI for data science. This is the first example that we want to share today. It's called MLentry, and same as TESS, the one that Steffen presented for training materials, it's also a registry, but in this case, it's a registry for machine learning models. What we are doing here is aggregating information from multiple machine learning models repositories, putting them all together in a harmonized way using schema.org, providing this information as an RDF, link open data, and on top of it, creating an elastic search so the REST API and the interaction with the user is easier. We are doing this because we have seen that there is already quite a good number of machine learning repositories, but there is no registry so far. And having the data harmonized in a registry will make it possible to find similar models, for instance, more easily than if you go and try to compare them, each of them for separated on each repository. So the next example that we have is MAPLAN, which is a registry, again, for research artifacts management plans. You probably have heard about matching actionable data management plans or data management plans. It would be great, and I would be really happy if you have also heard about software management plans. There is also a metadata layer for software management plans. That metadata layer is the matching actionable software management plans that it is created on top of schema.org and is reused in CodeMeta, and it will be integrated into BioSchemas. What is the idea here? We have data management plans that create some metadata for data sets. We have some software management plans that are creating some metadata related to the research software. What we want is to make it easier by integrating these management plans one to each other, but also to providing a support via RDMO and providing the support to extract as much metadata as possible from existing sources. For For instance, GitHub, if you have your software repository there, it's already providing a lot of metadata. So there is no need for the person using Maplan to enter all that metadata all together or whatever they have in RDMO. The idea is that we will create an extraction and we'll provide a registry for this metadata already harmonized and connected to other research artifacts. If we want to see how it all connects to each other, we can go to the next slide and see the big picture of the NFDI for Data Science Gateway. This gateway will be connecting different data sources, either directly going to the data repository or via registries, as the ones that I just mentioned. And the idea is to present users with a very comprehensive view of all the research artifacts that are related to machine learning models. So this is the big picture of NFDI for Data Science with the different partners and the different services that are provided, and all of them coming together in the NFDI for Data Science Gateway using schema.org for harmonizing all the information collected. And with this, I'm finishing my bit about NFDI for Data Science. We are moving now to Gabriel with FAIRagro.
Yes, perfect. Thank you. So I'll now introduce what we are planning on using schema.org and bioschemas as well in FAIRagro. So I'll present the ideas that we have and also give a little sneak peek on the current state, what we are working on. So as a quick introduction to FAIRagro, we are the NFDI consortium for ecosystem sciences. And as you can see here on the left-hand side, those are, you could say the perspective levels that our different use cases have on ecosystems. And you can see it starts at the bottom with perspective on genes and moves up to a very, very high level perspective on regions. And on the right hand side, you can see all the different research disciplines that are part of those use cases. And you can see those are very heterogeneous. So we have very different kinds of data that have very different kinds of requirements regarding the metadata. And one of the reasons we use schema.org is for harvesting and harmonizing those different metadata sets, I'd say. So what you see here is part of our infrastructure that we are developing. So aside from another big part of our project are the research data infrastructures. You can see as those green data silos here. And those are very essential services for the researchers to publish their data sets and describe them with metadata. And those different infrastructures have very specialized services for their community. So for example, Bonares is a repository more focused on soil data, for example. IDA PGP has more genetic data, and this is very different kinds of data. But what we want to do is develop a central search service. You can see on the right hand side of the slide that is this one-stop shop basically for searching all those data sets in a central place. And for making this available, we need some kind of harmonization between the metadata of all those research data infrastructures. And what executes this is the middleware you can see in this cog here. And the middleware needs to harvest the metadata in some kind of way and harmonize it to make it searchable. And this is what we use schema.org for, because we have 5 infrastructures in the first implementation phase planned, and 4 of those 5 infrastructures already use schema.org as some kind of markup. So our first idea of a basic middleware that we implement is harvesting those schema.org representation metadata and passing them on to the search service to make them searchable. On the bottom, you can see those orange data silos. Those are infrastructures planned for later phases in the project. For example, weather data from Deutsche Wetterdienst or other cross NFDI consortia infrastructures. And having a broad community relying on schema.org or bioschemas would really help in making interoperability more straightforward in the future for integrating other different research data infrastructures. So this is basically the first thing that we are doing with schema. And the second thing that we are doing is not only trying to harvest what is already there, but also improving the findability concerning the domain specificity of the metadata description. And what that means is when when discussing with our use cases on their metadata needs, we learned that there are some entities, as we call them here, that are not represented yet in schema, or not specifically represented in some kind of way. You will see with an example what I mean later. So those entities are crop and soil. Those should be pretty clear. We have use cases on pest and disease data. So they are interested in diseases that of plants and pesticides that you can use against them. And we also have a use case on models. Those are basically crop models that try to predict crop growth, for example. And we also have a use case that uses sensors for non-invasive phenotyping. So basically they use the sensors to measure some kind of phenotypic values for plants. And those are all entities that we would like to model in some kind of way with schema, so we could increase the findability of those entities. The idea that we have is reusing existing types and properties. Those were the building blocks, if you remember, that Leyla introduced in the beginning. We want to reuse those that exist as much as possible, because this is in the spirit of FAIR, you could say, to reuse other things. And it would also make sense to have like a broader applicability, because different communities rely on the different on the same standards. And this extension that we are trying to do is based on the schema.org extension mechanism, because schema.org is a community-based approach. And one of those extensions is bioschemas, which you already heard about a little bit. And because bioschemas and FAIRagro have some overlap in their domain, bioschemas for life sciences, FAIRagro with agrosystem sciences, we decided to join bioschemas as a community, because the overlap, and also because there are already processes in place on how to develop extensions. I have now some little examples on what we are currently working on. So what you see here is an example data set. This bubble in the middle called entry 1060 is one specific plant, one crop. And one way that we could go on modeling this is having this crop as a type, as a kind of biochem entity. Leyla mentioned biochem entity in the beginning. Basically, you could see this as like anything that is some kind of biological or chemical entity, and a crop is this kind of entity. And by using this biochem entity type, we would have different properties that we can use to describe it. For example, this is the name one here. It's a Triticum aestivum, which means this is wheat as a plant. And we have a taxonomic range, and this links to concept of wheat. In this case, this is agrovoc, which is an agricultural thesaurus. And so we would have the information that this is a wheat plant in a machine-readable way with this link to agrovoc. If we would model crop in this way, we would only use existing properties, because we use biochem entity and those properties I just mentioned. What we would need to do then is provide some kind of recommendation on values that we want to use for the taxonomic range, for example. So this would mean we could aid users in saying, okay, you want to describe crop, please only use this vocabulary or ontology that we provide you with for describing the taxonomic range, for example, and then we would be fine in modeling crop as a biochem entity. Another approach that we are thinking about is not modeling it as a biochem entity, but as a crop. And this crop would be a new subtype of biochem entity. You can see here those green additions. What this means is in an extension, we would create a new type, so a new class, you could say, that is crop. And this class is a subclass of biochem entity, which would mean that it would inherit all the properties. So again, this crop entity would then have a name. It would have a taxonomic range, the same as before. But what we could also define with this new type is new properties. And this is the one you see in the bottom, variety here. We could provide additional information. In this example, it would be that this crop is of a specific variety called portus, which is a more specific information than the taxonomic range. And what I want to show is that it really depends on what kind of search queries we would want to make possible with the extension, because we talked to our use cases, and for many of them, having the possibility to search for a variety as well as searching for a specific species would be valuable. So this would be a way how we could model this. And exactly on how we want to do this, we are discussing in a new working group that we started earlier this year. So this is a agri-related bioschemas working group. And we have monthly meetings where we talk about basically the requirements that we collect from our use cases and what would be the best way to model those examples. And we're currently working on preparing our formal group creation thing. And for this, we are also refining our use case requirements a little bit more. We are starting with crop, what I just showed, soil and pest and disease entities in the near future. And as everything around bioschemas and what we are doing here is a community thing. If you are interested in joining and contributing to the working group, you are highly welcome. So just reach out to us and you can join and start working with us if you are interested. Okay, so that's my part. Now I'll pass it back to Steffen, I think. Yes.
Thank you. And that'll be the example specifically we have in NFDI for Chem. Next slide, please. And one specialty here is that we have a federation of services. And at the very left part of the slide, you see we start collecting data already very early on in the laboratory in the electronic lab notebook. And this happens to be called Chemotion and is developed at KIT in Karlsruhe. And then upon publication, people move the data to the repositories. There is a corresponding Chemotion repository, but we also have Radar, NMArchive or Mass Bank for specific data types. And that's because we are dealing with molecules, reactions, and their characterizations. You also see here that there is the connection to the terminology service that Roman showed in an earlier NFDI talk, which is carrying ontologies and terminologies from different disciplines. And also we have the search service that is harvesting the metadata, very similar to what you have heard before. Next slide, please. So in chemistry, we have 9 types available from the SchemaOrg and bioschemas types. And as Gabriel showed earlier, there is a bit of discussion that needs to go forth and back, how you actually map your information and metadata onto these existing types. But in the end, we have these 9, and you see in the table for the different repositories which of them actually support the different types. And then the metadata can be transported either as HTTP in, for example, the HTML pages that are being rendered, but also, and that's something I'm going to show in a moment, using the OEI PMH protocol, which is very well known in the libraries and archives corner. And specifically, we are developing the NFDI for Chem search service because that shall also be able to search something about chemistry. Next slide, please. So that is the NFDI for Chem search service. People familiar with it might see that it's based on CCAN. CCAN is harvesting the data sets from the different repositories, and then you can search and display a specific entry. And the entry will be able to show you the related resources at the bottom. And the tags that we have there in the faceted search, they can be powered by the ontologies or defined terms that we have in there. Next slide. And I promised a word on the OEI. It is possible to embed the JSON-LD markup not only in HTML, but you can also put it into this Open Archive Initiative protocol for metadata harvesting, and that can be then harvested by CCAN. And what is really interesting is that there are possibilities to use XSLT transformations to move that into other kinds or syntax of metadata, for example, into a datasite, which is then required if you want to ingest things into open air. So I found that very interesting because it really allows to bridge to other worlds so that more people are able to get their hands or software onto your metadata. Next slide, please. And here is another example of how you can use the metadata in something else, namely the knowledge graphs. So the JSON-LD can be right away imported into, for example, GraphDB. It's also possible to convert the JSON-LD to RDF or Turtle beforehand. And such visualizations really help to harmonize the meaning of the types and relations that you have in there. It shows you what cross connections you might have also between data sets from different repositories, for example. They can be queried with Sparkle language, also across repositories for more complex queries. And an idea I would like to show and present is if that would be a vehicle that could be imported into a larger NFDI knowledge graph, because in the section metadata, we do have that working group on knowledge graphs. And there is a base for NFDI ideas of a knowledge graph. So let's see if that materializes in the future. Next slide, please. So I did mention the controlled vocabularies, and here at the top right, you see an example of a defined term, which is also a type that we have in Schemaorg available. And this can be filled by the information that we have in the terminologies in the terminology services. You can right away link out, you can use their identifiers, and also concepts like same as, if there's different ways to identify the same thing. There can be validators, as mentioned earlier, that can check if a term is coming from the recommended terminology and not something totally disconnected. And these defined terms can then be used in the search services, as I presented, to, for example, build up a faceted search. Next slide. And this is another corner which shows how we can bridge between the bioschema world and established worlds, like, for example, the datasite schema. So datasite is great because that's what you have for all the datasets that have a DOI. But if there is bioschemas, you somehow need to tell the world that there is additional metadata, and that can be done via the related identifiers. So this is something that we are also currently fleshing out, how to actually really do that, that we can specify the related identifier. And now we need to agree with people whether the schema type is a JSON or whether to call it a JSON-LD, whether the schema is a schema.org or something else. So any suggestions there are also highly welcome, and otherwise we'll flesh it out between the Schemaorg and Datasite people. Next slide. So that leaves us with the summary and outlook. Leyla, would you like to round up? Otherwise, I'll just continue with our last slide. And basically, I hope we were able to convince you that there is established metadata schemas in Schemaorg, Science Schema, and Bioschemas that can be integrated into, for example, web applications and repositories. They allow for more domain-specific metadata than generic schemas that we have seen. There is a vibrant community, which is actually having the community meeting right now as we speak. There was a bit collision of appointments there, and it's already used in several of the NFDI consortia, not only the ones that we're speaking today, but a few more, and also in the European Elixir Life Science Network. We can integrate the controlled vocabulary that we know from the working group on ontology, harmonization, and mapping. It allows search services, which is relevant to the working group on search and harvesting, and it could feed into knowledge graphs, which is applicable in yet another working group that we have in the section metadata. And with that, I'd like to get to the last slide and say thanks everyone who was involved. You see the slides are out there, and thank you for your attention.
So thank you very much for this interesting talk. And with that, I want to say goodbye to those who watch the stream on YouTube. In our next episode of our NFDI talk, Dr. Katja Klemm will talk about the development of a research data management strategy for the field of sports science. So I hope to see you there in April. And now I will stop the stream.